let's talk about why this is unfortunately not the case and why we cannot use data-driven signals directly as a proxy for performance. So I'm going to build the case here based on this plot. This plot is quite heavy, and let me explain it step by step. So what you see here is we're going to try to predict the change of model performance, here defined as ROC AUC or ROC, area under the ROC AUC curve. And what we're gonna do here is we're gonna basically took a lot of data sets and we measured how they change and whether we can use some kind of data-driven signals to actually predict that change in performance. So the easiest way to estimate model performance is to just use the test set performance. And what you see here is basically a straight line. It's a perfectly straight line that goes from 1 standard deviation to 10 standard deviations, where the model assumes no change. So our error must use just a fancy name for squared error that we used across different data sets. That's why the name is slightly different. But what you need to know is we're looking at the squared error of our performance estimation and the actual change, mean squared error, root mean squared error of the actual performance estimation and the actual change of ROC AUC. And if we assume that there is no change, then the error in our estimation is going to be just straight equal the actual change, because we're assuming that the performance is constant. And of course, we want to do better than the test set. If we cannot do better than the test set, it means that our whatever algorithm we have does worse than just assuming that there is no change in the performance. It's, of course, not something that we want to use.